Did you forget about this? I didn't. This has been haunting me every single day for the last 3 years. I have literally thought about this every day, and it has bothered me each and every day because I've wanted to get to it. WARAN. That means small software. Microsoft. So this is a fan tester. The challenge has been balancing everything else in the day-to-day reviews while also trying to learn something crazy complicated. And every time we'd interrupt that for a major GPU review cycle or CPU cycle, I'd have to start back over again because I'm not an expert on fans and testing them. And the challenge with that is that every time you interrupt a learning process before you've actually cemented the knowledge you're trying to gain, you're reset to zero. But we finally made it to making a video with actual testing in it. So, mission accomplished. We had this customized from Lawnwind's factory, which we've toured and filmed separately. We'll link that below if you want to see some of the test equipment in their testing playground. Our customizations were to support fans up to 200 millimeters in size. We paid full price for this, including shipping, and at the time, it was the most expensive testing equipment purchase we had ever made. It was also our first large test equipment purchase. But what I didn't know is that it'd be the most complicated one. So Vitaly, let's just film this. Watch out for the this is our computer case graveyard. We're gonna donate them. They'll get used. So we're gonna turn the machine on. This is an air compressor. This is hooked up, it's already powered on for noise reasons, pretty quiet though. And then over here, we're gonna flip the breaker to the machine itself. So that's pulling 220 volt. It's got a special plug at the back for that. And on this side, we've got the Star Trek bridge button panel. It is now on. We're gonna flip it to manual mode, which is what that is. And what I'm gonna do is hit all these buttons, and he's gonna point the camera through here, this window, which will show some of the valves opening. Now, part of this is that there's multiple pieces to doing fan testing. And so about 18 months ago, we also debuted our hemi-anechoic sound chamber. You can get your shot glasses out for that. That's become a thing on our channel now. And that chamber is a large part of fan testing as well, because what we need to do is collect very accurate noise levels because fans are pretty quiet. And if we're testing them in isolation and we want to have a 1 meter sort of ISO standard distance, then we need a very quiet room. And so this has been a part of that. And we needed that ultra low noise floor to be able to fairly noise normalize for cases, coolers, and fans, because world ambient outside and even the tiniest bit of background noise with a fan can create an unfair testing environment. And that's a story for another time, but it speaks to the core issue with the fans as well, where I got locked up with paralysis to get it right with the fans. This is part of that because we need it to be a controlled environment where every now and then people will post comments and say, why use such a quiet room? It's not a real world environment. And the problem is the day-to-day noise can fluctuate so much that things like lower frequencies that have a longer wave that penetrate concrete and buildings more easily can start to cause, you know what, this is the focus, Steve. This is the problem. This is why we didn't get to the fan testing for 3 years. It's because I find the rabbit hole and then I go down it, and then we need to just go back to the fan machine. We'll do this another time. So the point is that that chamber, it's up and running and we're using it and it's been working great. And that laser scanner over there, also up and running, but we got both of those things way later than we got this. So why does this take so long? Well, it turns out that fans are incredibly complicated and physics is hard. And I don't understand physics very well for computer fans, but I'm trying. And that's why when we got the fan tester, I bought these light reading materials. Physics, the basic quick reference, like you have a test in 15 minutes version. The mechanics of fluids, I got this one, 9th edition, far better than 13th or 14th, I'm sure, if we're going by Intel naming. Heat exchangers, that was pretty cool. I learned about things like Bernoulli's principle. What I didn't learn is, do you pronounce the L's or not? You can let me know in the comments. Intro to fluid mechanics, and okay, that's not supposed to be in there. We brought you this video. You can use our coupon code ABOUTTIME at checkout for 10% off anything on our store. That's about FKN time. We recently restocked a ton of our brand new GN dice kits that we launched a few months ago. These include our 7-piece sharp edge resin dice, which embed e-waste inductors within them and which we've tested for randomness. We also have the Snowflake the Cat dice, where CEO Snowflake can be found internally inspecting each die. The tabletop gaming dice come in high-quality wooden boxes that we designed with latches and an integrated roll tray, plus playing cards, and an RNG table that I personally wrote for your tabletop gaming. If you want to express your disappointment in us taking so damn long to get this operational, you can also grab one of our limited Disappointment Tour t-shirts, which we're running low on, also disappointingly, so you better get one before they're gone. Otherwise, we'll need a new coupon code for double disappointment. Finally, consider grabbing one of our silicone soldering and project mats with high heat resistance and an integrated storage compartment with tool sorters. All of that is on store.gamersnexus.net and directly supports us. Remember to use code ABOUTTIME at checkout. But the point to all of this is that fans are complicated, and I truly had absolutely no idea how really complicated they are. We've had a couple of interviews with Noctua's Jacob Dellinger, who's done a great job of talking about some of the basics, and it's a great series if you haven't seen it. This is the most important book we have here, though, which is the manual for the tan festing machine. We're gonna run some tan fests now. Should probably work on the pronunciation before let's just shelve this for another 3 years while I work on that. So to get anywhere with this, because again, I was just paralyzed by making sure we get it right, because this is the type of machine where I've said it before, but it produces very complicated data with really no other tools that we have to do the same level of validation. This is the best tool we have. And so that means if we misuse it, then we would have very wrong data with extremely high confidence, and those are problems. And so to get this off on the right foot, we did the same thing we did for the hemianechoic chamber. I contacted Aris Betiopoulos from Hardware Busters and Cybernetics, and Der Bauer from Der Bauer. Aris runs a third-party testing lab that provides ISO-certified validation services to manufacturers. And he's also the most prolific power supply reviewer for consumers. Der Bauer runs Thermal Grizzly, but also has an engineering background. We respect both of these peers and went to them for some QC of our first attempt at using the fan tester. Aris in particular is a good gut check here because he also has basically the same machine. We might have some slight differences, but it's more or less the same. So I need a training level to start on because this is all new to us. We want to start and sort of build iteratively. And so what we're doing today is a pretty cool test, which is something I've actually wanted to do a really long time. So these are different case front panels that we had custom made. Montech made these. So a quick thank you to Montech for making them to our spec. And we basically went to them a couple of years ago now and said, here's the idea. Case front panels, sometimes it looks like they're really heavily perforated, but they perform terribly. You take the front panel off, way better. And so let's explore that. And so they've created a couple where this, if we get a shot of the bottom right corner there where the tape is, this is according to their sort of calculations, a 63% porosity. So if you look at it, the material here, it's really flimsy. You'd really not want this on a case. This isn't something they actually make and put on cases. You've probably seen it on some. This is more of like a power supply area type of porosity, but it's also very flimsy. Now, one of the other big downsides with this is dust ingress, which we're not getting into today. But the thing to remember is that 63% number. And this all relates back to fans, but it also relates with cases, which we have a ton of data for, and that's why we started here. I needed something I was familiar with to start learning. And so this is a 13.4% porosity, and this one, so you can see that percentage there, but if you look at the actual panel, I mean, that is a really closed panel. It looks perforated, but that is mostly metal. it's only 13.4% whole. That's the porosity part. So we'll test that. And what we're going to do is mount these different panels. So they go up to, this is 22.7, this is 32.6. I'll just read them off. This is a 51%, and this I think is a 56.25. And so what we're going to do is, if you come around here, this is a case front panel. So this is from a Montech case. I think it's maybe the X4 panel, I'm not sure. And what we did is put the 120 mil fan on here. So this is a Noctua NF-A12 by 25. Put that on here, put the front panel, and then these were built in a way where I can socket these. And so we could socket these in and sort of swap them out to then test the porosity impact on the fan's performance. And so this is kind of a cool academic exercise where we have over a decade of thermal data for how this impacts the CPU performance thermally. But what I want to see is how does that map to fan data? And the reason, again, so a couple of reasons we're starting here, just to get everyone on the same page. First one is I need to learn what I'm doing with something that's a little safer to learn on, that I can send out to some peers and get some feedback on, and that I can put out to the public, to you all, to get some ideas for presentation, for chart data. So as a quick example, some of our sort of most well-known charts now by the audience were actually audience ideas a long time ago. One of them, noise normalized testing, that came from a comment on a video probably when I was still working out of my mom's house. Another one that we do is FPS per watt efficiency. That came from a comment on a video. And so we're putting this cool stuff out there. And then hopefully some of you will have some ideas where you're like, hey, what if you cross this variable with that variable? What do you get? In addition to just sort of the PQ curves you can get from a fan. So anyway, that's kind of why we're doing this. The other thing though is I want to intersect the thermal data with the fan data, and probably some of the next pieces we're doing, to see how do these relate to each other and start establishing an expectation for, so we get all these numbers from this machine, how does that sort of manifest in these different common everyday scenarios? A case, a radiator, a CPU tower cooler, and that's kind of what we're trying to build as I'm learning it. So it's a really cool way to do sort of a learning exercise that applies to real world testing. But if we go back to the machine, so right now we have the fan mounted to the front, like I was saying. This fan is on a big acrylic plate that the company Lawnwind that makes this machine made for this 120 mil fan. If we open the drawer of treasures here, we have a bunch of different sizes. So I have backups of all these too in case we break one or something. So that's a 140 millimeter fan tray or mount. And then we've also got these other ones. I mean, the most unique ones we had made were this 150. Specifically, this was an NHD G1 that I had made, and there's a reason for that I'm not going to go into yet. We have some 180s and some 200s. So way in the back here, we've got this massive 200. You can see a cheese grater bunch of holes because it's not a standardized screw placement. So this I'm excited about because I haven't seen a lot of data on this, and we had this custom done for, so this specific fan machine, testing machine we had made was custom made to support that, and we've got 180s as well. But the interesting one is actually this. This is for calibration, and it is known as the orifice tester. And we're gonna need a better name for that, something a little less biology class sounding. So we'll work on that. I just feel like saying orifice testing over and over is probably going to generate a lot of comments. Leave your ideas below for the new orifice tester name. Be appropriate. So this, I shouldn't have said that. I've made it worse. This is what we're going to use today as well, where we'll mount this to the front. And so the way this kind of works is all this needs to come off. This tape, so this is a GamersNexus patent pending solution. We filed it with the USPTO, you can look it up. And it secures the panel. The patent pending solution is modular. That's kind of the beauty of it.
Also toolless.
It's toolless, that's right. Good point, Vitaly, no screws. So what we're gonna do is just pull this plate. There's one more that goes up here. I'm gonna leave it off because we're gonna put that case panel back on. I've also learned that these clamps really hurt if you pinch your finger. So the plate can now go on. Now, normally to run this for full calibration, I would mount this last one. We're just doing a demo right now. So that's how the swapping of the plates works. There's a couple other things I'll show you on this machine before we get into some of that initial data. So over here, we've got the air compressor. We bought this one. It met the spec we were going for. So Patrick Stone picked this out for us. And it's extremely quiet. It's been on this whole time. Can't hear it. Every now and then it'll sort of vent and it's pretty loud. But this plugs in, so through this cable, or this hose, we have the tube running over there. You can see going through the ductwork. That's connected to the machine. There's a certain spec that it needs to be at, which we've got it set to. There's a bottle down there to collect any accumulated water that drips down. And then we maintain the air compressor as well. In the event that it gets any water, we make sure it stays empty. Down here is just the power in from the wall, and then the breaker. So this down here is a counter blower. So this is a fan that's inside the fan testing machine. And this blows counter to the fan that mounts to the front. And so this is used to generate basically whatever resistance we sort of want to simulate. Now we're still gonna test things like different radiators on here, but that's something that Aris was teaching me about specifically, where he was explaining how, well, you know, this can generate the resistance you want to start evaluating how the fan behaves under different conditions, where basically when this counter blower spins, what's happening is this tube is where we're getting the air movement. So that blue pipe at the back, that's exposure to the outside for the counter blower. And then this is also connected to the counter blower. So that's kind of where we've got the access to external air is through those two, well, is through the back tube and then through the floor. So that connects to the machine. The other equipment on the machine includes this benchtop power supply, which we need to turn on anyway. So we've got that plugged in, turned on. It's already configured to a max of 14 volts, but it typically runs at 12 for the fans. And then over on this side, which we've already turned on, is the actual machine with all the readouts. So a couple things here that are interesting. We've got millimeters of aqua, so that's pressure. So we have a couple different gauges that talk about that. This is this P56, that's delta pressure. So that's what that is. Then we have temperature readouts too. So you see there's a T5, a T8. So this is reading 21 degrees Celsius, this is reading 20.5. They're in different places. And then we also have TD and TW. So these are temperature dry and temperature wet. And so we're about 21 degrees Celsius for just air. And then the wet probe is reading 16.7. Now that is for part of the equation. We'll come back here for humidity, which the machine also monitors. I was gonna say, I don't know if you can get back here with all that stuff. Well, he's done it. He's, you know, this is, I really wish the people watching the video could see how Vitaly has crammed himself in here, because the camera equipment is not small. He's wearing a giant vest. So this is where we have the, those two probes. So this one here, that's a temperature probe, this metal rod, that's a thermometer. That's TD, which I'm calling temperature dry. And then this is TW, so this is temperature wet. And if you look in there, you can see there's that white rag that goes over it. So that is referred to as a sock, as far as Lonwin's called it with me. So that is actually in this sort of bucket, which I need to fill again, of just distilled water. And so that's soaked, and that gives us the two measurements, which are useful for determining the humidity when the machine's running. And we've got this little cap for filling it and all that stuff. And all this is just wiring for the rest of the machine. So we're gonna try and get out without anyone getting hurt. That's most of the basics. There's a couple more things. I mean, this thing over here is just an arm, and what it does is it holds actually a really nice laser tachometer. So this is a laser tack that we can use for measuring the RPM, or we just go through PWM. So right now I have it hooked up for a 4-pin fan, so we don't need this. Now I have been using this to validate a lot of the RPM readings the machine's getting. I've come to the conclusion that this fan and this machine, they're like pretty much perfectly accurate with the external measurement, so I've stopped using it for this setup. But my plan is to keep using it for initial setup for methodological reasons. So anyway, that would mount up there, but what we're actually gonna use is you can see the PWM frequency and duty percent down here. So it's 25 hertz, and then we've got 100% duty cycle, fan stops spinning because there's no test right now, and that's what we're gonna use. Let's get the software going. So this is the software. First thing we need to do is zero it out for a test. And so that noise, whatever of it picked up, that is the machine kind of going through, all these light up, and it's starting to test those different, basically they're like vault doors in that window. So that's what that's doing. So that'll run for a little bit. And what that's doing is zeroing the numbers out, like this one here, just to kind of get it prepped for testing. Okay, so now we'll launch the software, and that pops this up. So this resembles, if you point to the wall over there, that poster, resembles that. And what that's telling us is the different ways that this tube can be used for testing fans. So as you see, fan blow in. It's pretty clear. That part was easy to understand. So fan blow in, variable exhaust system. Now, a couple other options here, the way this is configured currently. System resistance curve is another one. So you could use this with like the orifice tester. This is, I don't know why I said you as if this is not a tutorial. And then this is a server that they're depicting here. So you might use it to detect, to test for resistance from a particular chassis or something. And there's also airflow and thermal resistance that they've got marked as TRC. Now, this is where, fully transparently, I'm not really sure where I would use that yet, because it's just not something I've needed for the test I'm doing. So this is part of the, we are learning how to use all this. I have not used TRC yet. I'm not sure when I would use it, and so I can't really tell you what it's for. But now the rest of these, I'll click on them for the pictorial representation. So you see here, they've got the fan mounted on this side, and it's pull. So this is now exhaust. We're using it as push at the moment. Same thing, servers over here, resistance curve going through, and then airflow resistance TRC, which I'm not 100% up to speed with. So anyway, we would click through, we'd choose something, we mounted that plate, so we'll do that one, and then we'd basically set up the parameters under settings and run the test, and the machine spins up and it starts doing its thing. So those are the basics. Now, again, the machine's very easy to push buttons on, it's easy to operate, it's hard to fully understand and appreciate the data. And so we're going to get into some of that today. It's going to be our first attempt at this. These are all experimental charts, and I'm pretty happy with the test case we have, and also pretty happy with the data we've pulled so far. So now you can hear the counter blower is doing its job, and can actually feel the air movement in this tube back here. So that's kind of how it works. You can even see up front here, we've got this, well, now it stops, but when it spins, it gives you a readout. That gives us a readout, and all these numbers will change in real time, so we can stay dialed on these things for a minute. Where it's measuring currently, it's hitting a target flow, target CFM, and what it's doing is measuring the pressure at those different target CFMs for the orifice plate tester. So I think it's going to do 4, 8, 12, 16, all the way up to 40 CFM, and it's going to spit out a bunch of numbers in this table that tell us what the pressure is at those different flow rates. And it's also creating a spreadsheet just with Excel down here. So it's probably about to log the first set of results. So it's created the template. It's going to start filling in the data as it collects it. But we'll let this run for a second. So if we cut back in here, check over here for a second. So Vitaly, see if you can see that bottom right circle right through there. Yeah, I don't know, did you get that? So that was closing off. So basically it's gone through and it's decided that it was gonna close one of those sort of vault doors as it's continuing its test. And this is all to evaluate the pressure against the flow rate for the orifice tester. So you can see it's starting to create a line here. Now this is missing a lot, it's not done yet. But we've got 2 points, which I guess technically create a line over here. We have our first 2 measurements. So we've got a Q or CFM of 4.0 for that first one. This is a target. And then we have approximately 8, approximately 12. And on the left of that, we've got pressure in millimeters aqua or water. Sometimes you see that mmH2O. Yeah, and so then it's just gonna keep iterating here. And now we've got a 16 and it just keeps going and starts to build the data. And then this line will plot as we go. And I'm not sure if it's updated Excel yet. Not yet, it's gonna do that at the end, I guess. And then over right here, you can see I've got the settings. So this is where we got start 4, step 4, stop 40. This can be reconfigured however we want, and it tells us what it's currently doing. We can tell it how many passes to do. So if we wanted 10 passes, we could do that. You can see now it's running 28 CFM. Over here, it's running 7 out of 10 tests, so it's got another couple to go. And yeah, that's pretty much how it works. Then this panel here is a representation of the physical panel on the machine. So they're redundant. You don't really need both, but it's pretty cool to have both of them. And this is just going to keep going until it's finished. So this is an automated fan tester. It still requires some setup. You have to type in some parameters for the fans being tested. All that's handled in the manual we have, but it's kind of the concepts. Now, I think it's worth getting into the why this test a little bit more. So talking about those panels, and then we'll get into the first round of data. Hopefully this primer has been fun so far, because this machine is so cool. I really like working with it. There's the Excel sheet. Same stuff. And then we take that as a CSV and start doing stuff with it. So, yeah, let's get into why this test. This lawn wind machine can be used a lot of ways. Long term, we'll be using it in a head-to-head fan comparison, and we've already started. That'll include thermal tests, PQ tests, and noise tests, which we're rolling out in building blocks bit by bit. Eris's team is actually visiting us next week to help train us. The reason we're starting with SRC, or the resistance curve here, is because it's something we can learn on. As a part of that, we're going to do a focused feature test today to let the audience start thinking about data presentation with us. You'll be involved in our process. All right, first chart. So, massive disclaimer. This is all experimental. That means I don't fully know what I'm doing yet. I think that we're at a point where we can start publishing stuff, and we have some base confidence required, and it's enough where it's like, okay, we feel like we've cleared the bar to where it's not totally irresponsible, and we have to start experimenting with this to learn. So we're feeling pretty good about it, but again, that disclaimer of we'll let you know when I feel like I'm personally at a stage of knowledge with all this where we can start publishing fan comparison charts A/B and say, yep, we stand completely behind this data and we're happy with it and we think it's good. As soon as we hit that point with 100% confidence, we'll let you know. But until then, we're feeling good about it, just not fully there yet. It took literal years to build our GPU testing to where we are today. I mean, it's taken 16 years to get to where we are today. So first thing we're gonna do is with that orifice plate tester, if you get one more shot of the front here, and we're mounting the case panel to it. So this is removed for that. Now that means there's a very tiny gap up here, but it's really not much. And what I did in the testing process to solve for that is I took this kneadable eraser and I just jammed it in there. So anywhere there was a gap, I filled it. It's way less than like 0.5 millimeter gap. So jammed that, put the case panel on it, swapped the mesh plates that were in it, and we ran the test to get a pressure measurement by using the counter blower against a known CFM. Let's look at it. The aperture plate without any obstructions is first. Here's the chart. The aperture plate shows a clean curve that trends higher on pressure as the CFM increases, which is different from what we'll see in the fan-specific tests where pressure and flow on a line plot are generally inversely related. You get that PQ curve. This next line shows the plate with a front panel mounted to it. There's no fan here. This is the panel with a 13.4% porosity, meaning that only 13.4% of the total area is whole, with the rest being metal. We asked Montech to make this as bad as they could while still having holes in it. The 13.4% porosity trends very high as compared to the open-air orifice plate test. This is where we get into one of the more important transparency notes. We know that these numbers are right, but what I'm not 100% certain about is describing them linguistically. Originally, I would have described this as the pressure required to hit 40 CFM. So this is an example where we'll just learn the best descriptors with time. When I asked an engineer in the industry if this description made sense, they suggested to me that a more accurate description for this might be, for example, that in order to hit 40 CFM, the 13.4% case porosity resulted in a pressure drop of 141 millimeters H2O, rather than saying the, quote, pressure required to hit that CFM. So we'll roll with that language for now. While that's what we saw at 40 CFM with the open aperture, for the same CFM, we saw 21.6 millimeters H2O. We knew such a blocked panel would be bad, but it's crazy to see just how much worse it is. It's also interesting to see how much they diverge as the target flow increases. The next line is for 22.7% porosity. This one sits evenly between the open and the 13.4% results. The 22.7% porosity resulted in a 78mm H2O pressure drop at 40 CFM. At 20 CFM, the two are closer together at 20.6mm H2O versus 37.4 on the more restrictive panel. But despite this closing of the gap, the proportional difference is similar. We continue to see this effect with the 32.6% porosity, where the 40 CFM result is at 54mm H2O, and the 20 CFM result is at 14.1mm H2O. And this 32.6% porosity was one that a lot of panels used to run, or similar to it, about 5 or 6 years ago. We eventually hit the results for 51%, 56.25%, and 63%. 63% has comically large holes in an extremely flimsy, cheap-feeling panel that would break with almost no effort. It's not a good solution, and it's not good quality. The good news is that it's also not significantly better, with these three panels all producing similar results from 0 to 40 CFM target. At 40, the biggest to smallest measures pressure at 27.5, then 29.9, then 31.2 millimeters H2O. I asked an engineer to help explain some of these results to me, and I can't write it any better than the engineer did, so I'm just going to read their quote exactly, but the engineer did ask to remain anonymous. So this is what was stated to me. Quote, fundamentally, your air mover creates a pressure differential, and then depending on the pressure drop of your system, that pressure differential creates flow. What you're measuring is the pressure drop of the system. You can think of this in the electrical engineering analogy, where pressure differential is voltage, pressure drop is resistance, and flow rate is current. Pressure drop typically has a quadratic relationship with flow rate, just as you've shown here. Pressure drop is proportional to CFM squared if the flow regime is turbulent, proportional to CFM to the first if the flow is laminar. Very rarely, pressure drop does not change at all with CFM. Take, for example, a bubbling pool or aerator in some body of water. The pressure drop is always equal to the hydraulic pressure, so no matter what CFM you're running at, the pressure drop will always be the same. In all cases I've run into in consumer electronics, the pressure drop is proportional to CFM squared, as you have in your charts. There are some references to the Darcy-Weisbach equation as well, but we'll get into that in future discussions with engineers who are actually qualified to talk about what it means, instead of me just reading the Wikipedia entry. Next up is a 120mm test plate with a Noctua NF-A12 by 25 mounted to it. We then mounted the entirety of the case front panel in front of that, including its gap between the fan and the mesh. This will more closely resemble most modern cases, where there tends to be a gap between the actual fan and the front of the case. Generally, this benefits the performance. These results will be at max CFM and basically free flow from the machine's perspective, but we've added the panels. The machine can be adjusted to create basically any sort of resistance we want, but in this situation, we're externally providing the resistance with our own panel. It doesn't know that the panel is on there. So for that reason, we'll test this in free flow, again at max CFM, that the fan is capable of when obstructed by the varying front panels. Testing for this section will involve the fan running at 100% PWM signal. The RPM will actually become a variable, even in spite of this, because as the resistance in front of the fan changes, the RPM will change with it. This chart shows that, where the more restrictive panel is resulting in lower RPM. That's not news, in fact we've talked about this a lot in the past with our case tests, but the point is that we're not trying to control for that change here. We're viewing the RPM variable as a valid part of the test, because that happened in the real world too. In fact, we see this in real-world testing with cases all the time. In this chart, you're seeing a much less exaggerated change than we observed in the aperture testing in some ways. The 13.4% porosity result was terrible in a truly obvious way, showing the sharpest reduction in performance. Its max CFM was 54.52, with the 22.7% porosity drastically improving to 59 CFM. We observed another gradual improvement to 61 CFM with porosity of 32.6%, followed by one more jump to 63 CFM. And at this point, it asymptotes, and that's actually really cool. The results for 51%, 56.25%, and 63% porosity are all nearly identical. 63% benefits from a bump to 63.5, but that's not much change. Without the mesh filter at all, and just testing the fan mounted to the tester, the max CFM result was 64.43. There's one exception to all of this, which is that with a worse performing fan, it's possible that this sort of asymptotic results don't occur as early. Or in other words, a fan with worse performance might be hindered more by a 51% porosity than we're seeing here. And we have some results for that. This is with the same fan, but reduced to 60% PWM to hurt its performance. Again, we already tested the pressure heavily controlled with the orifice tester, so we're looking at the CFM here. The flow through the 13.4% porosity panel landed maximally at 35.12, opening up to 37.9 CFM with the 22.7% panel, then 39 with the 32.6% panel, and then 40.2 CFM with the 51% panel. This is where we level out once again with almost no change to the 56.25% panel and results within run-to-run variance at 63%. The fully open plate-only test had us at 41.79 for CFM here. As far as how this relates to real world, here's a good example with thermals. This is what actually set Montech on the right path with its newer, more open case designs. In our 2021 review of their Montech Air 1000 Lite, we said it was Air in name only. The front panel plus its filter were extremely restrictive. This is something Montech has really improved upon and learned from in ways which are commendable. In this chart, we tested the case stock and found a 51.7 degree delta T over ambient CP result in our old case review methodology. Removing the front panel improved that to 48.5, which would indicate that it's not too restrictive, except the real problem was that those small mesh holes with the low porosity overlapped with the small holes of the dust filter, also with low porosity. Removing both saw a massive reduction, down to 44.8 degrees delta T over ambient. That's a 7 degree improvement because the two panels were overlapping in a way that was bad. Opening up the front mesh more really helped with Montech's performance in the future. Obviously, you don't want to go full open, but what we want to see is as little change in the performance as possible. That means they're as close to sort of open air as they can be. This is from our review of a Cooler Master Half 500 released in 2022. This single chart contains a ton of variations of the case configuration, with the mesh installed on the Half 500 not to be confused with the H500, the H500P, or the H500M. They really like H's and 500s. We saw a 46.1 degree result. Removing the front panel brought it only down to 45.5, which is awesome. That shows us that the mesh on the Half 500 was minimally obstructive, and yet it was still fine enough to help limit dust ingress. The case had other problems though. The H500P on this chart is the opposite of this. With a heavily obstructed plastic front panel and limited side mesh, it ran at 56.9 degrees. Going to a mesh front panel improved it to 48.2 degrees, an 8.7 degree improvement. Looking at another case, this is the H7 flow chart. In this one, we saw a 47.8 degree result when stock that improved to 45.3 degrees without a front panel. This case used relatively large holes, but still had the thick metal in between to keep that rigidity. It wasn't too obstructive, but more than the mesh in the Half 500. So these charts give some ideas for how the impact is realized in the real world in thermal scenarios in different ways, depending on the porosity. But now we can see it in a much easier way, and it gives us a better appreciation for what we might expect and where the limits are for how much you can really open up a panel and have it still matter. So the way we can look at that now is flow and pressure testing, which is pretty damn cool. The reason this is exciting is pretty simple. We can show all this stuff with thermal testing, and we've been doing that in the case situation specifically, but when you start looking at fans individually, it gets really challenging to even see a difference sometimes, and because there's so many variables, namely that things like radiators, for example, can have different fin density. You might have different fins per inch, for example, or because case front panels can have different porosity, or whatever the application is. The tower cooler can have a different amount of fins in the tower. All of these things affect how the fan performs, and so that makes it really difficult to only look at thermal performance as an indicator of fan performance. That would be sort of nice because the thing that people understand the most immediately relatable, like how much better is my cooling with this fan mounted to the cooler? But there's so many variables that having the fan tester will allow us to more rapidly develop the PQ curves to look at the pressure against the flow, and then we can mount different things to it, and it gives us a really controlled, calibrated environment where you eliminate a lot of the other variables, so that helps. Now, we're still going to do thermal, but that's a different discussion for another time as we kind of get into that. So where we are right now is overall, I'm starting to feel good about the data that's coming out of the machine in that it feels like the numbers, we're getting those right. So I have checked the numbers that we have against some others, especially, again, a huge thanks to Eris from Hardware Busters. I've been referencing a lot of his work as we get through this, and the numbers are lining up. I asked Noctua to send us some of their data for this fan, talked to Longwen, and that part's, it seems like it's going to be pretty good. I think where there's going to be a learning process for me as I'm writing these is the language. So specifically things like phrasing the explanation of the data. That's going to take me some time, and that's where if you have comments about improving the precision of the language that's used, then leave them below, because I am going to be reading those for every single one of these to just try and fine-tune my understanding, my delivery of it, and that's just sort of the stepping stones part of all this. So as an example, I was working with someone who's providing some insight anonymously outside, works at one of the companies, and there was some phrasing where the way I was originally describing what we saw in that sort of that orifice tester chart was the hitting a CFM of 24 required this much pressure, and that was described to me as, well, it'd be more precise if you said it as to hit 24 CFM with the 13.4% porosity, there was a 54 millimeter H2O pressure drop. So stuff like that, where that's like the data was right, but my original language before we wrote it was not really the best representation of that data. So that's what we're going to be working on. I'm really excited about this. The reason it's taken so long, though, some of you who have asked, is because of what I just said, where it's like, I had to come to terms with like, okay, I'm not going to be able to just nail at 100% PhD level precision on all the language, all the understanding out the gate with the first content. So we're going to roll it out piece by piece. It's all experimental, and we are going to sort of keep working on integrating audience ideas and all that stuff. And then we'll hit a point where it's kind of like our GPU reviews when we test a video game, and been doing that so long now that we're pretty fucking good at it. So hopefully we get there with the fans as well. Anyway, takeaways from some of the data today. One of the interesting things was that way it sort of asymptotes. And so as it gets to like 50% porosity, we're in that diminishing returns area. Now this is just with this one fan. It's gonna be different for different scenarios. But with our test setup, the diminishing returns kicked in at about 50%. And as soon as it got above there, even up to 63, there wasn't really a huge change anymore. And certainly not worth the trade-off of the rigidity or the restriction to dust ingress. You start trading off a lot of things for very little gain in this controlled testing scenario. So that was cool to see, because some of the panels we know are in that 40 to 50% porosity range. Now that makes a lot of sense why they might do that based on what we saw. As for ideas for what we're going to try next, first of all, leave your requests below. Keep them like simple in terms of try to restrict your ideas to just like one variable to swap out right now. We'll do more complicated stuff later, but stuff I'm thinking about, I was talking to BuildZoid, and he'd really like to see just a bunch of radiators tested against sort of common fans, like maybe pick 2 fans, swap a ton of radiators through, look at AIO versus custom loop radiators, stuff like that. So that's definitely interesting, and that is a pretty controlled test. Thermals will come later. Noise normalized will come a little later. So we're going to start with, like, let's just pick something to just, dust filters. That's another great example, testing the impact of different dust filter designs. And so we're going to use all of these sort of micro tests, these feature tests, to then build into the A/B fan testing. And that was just, it was my learning process where this whole experience has been very like introspective of, okay, this is a very challenging thing. I want to do it, but thinking about I want to do this is not going to get it done. So how do we make it happen? And what I came to was, all right, well, the way I learn needs to be iterative. And so that's what we're going to do. And as we keep rolling those out, I'm very excited to get into the full-blown like bunch of fans on a chart test. And we can get into the true purpose of computer hardware reviewers, which is bigger bar better. And then you can take bigger bar better to argue on Reddit with someone about why your computer is better than theirs. That's all that really matters here. So anyway, a lot of fun and very excited about this. Lots to learn. Kind of repeating myself. Thank you for watching. To support us directly, you can go to store.gamersnexus.net and use the code ABOUTTIME for 10% off anything on the store while that code is active. And sincerely thank you all for your patience. For those of you who have waited years to see this, we're here. We're making it happen. And it's going to be super cool to combine the fan testing with the acoustic chamber that we've already been using, because that's like the perfect combination. So, all right, subscribe for more. Errors from Hardware Busters is going to be here next week, and he's going to help us out even more with it. So we'll publish a lot more on the fan tester basically within the coming couple weeks. And we'll see you all next time.